Welcome. Today I have more questions than answers. I was making a few experiments this week with three manifolds, especially with the homology sphere. It's a wonderful example of a three manifold. This is related to the dodecahedron. You can identify opposite sides of the dodecahedron and turn it. But you can also see it algebraically. It's just a three sphere divided by a group, this binary cosahedron group, one of the groups with 120, 14 groups there are with 120 elements. That's one of them. It's a beautiful group, and it's related to a Platonic three sphere, to the 600 cell, 120 vertices, and then you have 600 three-dimensional parts of space, simplices. So you can implement that and animate that. You can rotate it in 4 dimensions and project it into space. They're beautiful pictures. There are different ways how to visualize 4-dimensional space. Also visualize the three sphere using the Hopf vibration, something which Thomas Banchoff has first done. And so it's a sphere, right? We are dealing with a sphere, but it has the same cohomology than the sphere, but it doesn't have a three sphere, but it has the same cohomology than the three sphere, but it's not homomorphic to the three sphere. Actually, the fundamental group is just this binary group, so it has a fundamental group with 120 elements. And the first thing I wanted to do since a long time, actually since I started working on Wu characteristic, it's no problem to compute the Wu characteristic. A Wu characteristic is the same for any manifold, the same than the Euler characteristic, and the Euler characteristic of course is 0 for a three manifold. So this is an example of a three manifold, so it's no problem also with a computer to compute the Euler characteristic. It's no problem to compute the Betti numbers, the usual Betti numbers. What you do is you compute just these kernels of matrices. But what happens is, if you look at the higher characteristics, like the Wu characteristic, which is the second one, you also can write down matrices. These exterior derivatives, you have the Dirac operator, you have the Betti numbers, which are the kernels of these block matrices. Now there are 2D plus 2 blocks, right? So you have the 0 forms, you have the 1 forms. The 1 forms are given by all pairs, kind of functions on pairs, such that x is one-dimensional, y is zero-dimensional, or y is zero-dimensional, x is one-dimensional. So we look at intersecting pairs, and so the matrices are getting much larger here. And you can see that when writing down, there's this analog of the F vector is the F matrix, which tells you how many k and l dimensional simplices there are which intersect. And you see, for example, there are 6,272 possible pairs of intersections of three simplices. If you look at this and you write down these matrices, this is just too large, say, for Mathematica to compute. And what I was trying to do kind of this week, I looked at collapses. So there's a nice way to produce homeomorphic versions of a manifold. You take a manifold and you take a simplex, and then you just collapse it together to a point. And then what you get is you get a smaller manifold. If you are unlucky, then it's too small to be. For example, if you have already a very small manifold, like the boundary of a tetrahedron, which is the smallest two-sphere, and you collapse one of the triangles, you get something lower dimensional. One of the observations also I did, I don't know whether one can prove that, if you take a two-sphere, a simplicial complex which is a two-sphere, and you make these collapses, you always get down to the smallest one. It's not true for three spheres, and also here for this homology sphere. This is the smallest implementation I know of by Björner and Lutz. So I take this homology sphere, it has 392 simplices. And so but still kind of this, if you look at this higher characteristic, you can compute a higher characteristic, but the higher Betti numbers I have not yet been able to compute. And I suspect that actually it's not the usual, it's not the same cohomology than the three sphere, and that would be really cool. So I have seen here in this context that if you take this cohomology of a Möbius strip, you get a different cohomology than cohomology is trivial actually for a Möbius strip, and it's for a cylinder, it's not trivial. So it's kind of interesting. I think it's an interesting quantity. So these higher characteristics are related to topological invariance and not homotopy invariance. So that's the first question. So I tried, could not yet do that. I mean, it's just too small. I might actually try again on a supercomputer to see when I need just more memory. Another thing which I kind of have looked at last year, which is this analytic torsion, which is also a topological quantity, which I've shown for spheres. For these spheres, it's just depending on whether it's even or odd dimensional for F0 or for Fd. For even dimensional spheres, for odd dimensional spheres, it's F0 times Fd. So it's an interesting quantity. So I battled last winter, the winter year before, I battled with this. It's an interesting linear algebra thing. Why do you have this k here? And it's actually the super determinant, the super pseudo determinant of the Dirac operator. So it's kind of has a natural interpretation. These are pseudo determinants, these are not usual determinants because they have kernels here. Still, you can also do that in the context of a higher characteristic. You can look at that, and in that case, I'm also kind of, these are getting too large matrices to write down and compute these things. So this is also something to explore a little bit more. The third thing I just wanted to mention, because if you're in a context of questions, this is something looked at in 2021 or so. I think in the summer, I looked at again at the coloring of manifolds. So I have a general result for all manifolds. It's not very good, but it's true for all manifolds, all D manifolds. The chromatic number, and this is for graphs, the chromatic number is sandwiched between d plus 1 and 2d plus 1. Now, if you have a simplicity complex and you know what is the chromatic number, you cannot just take that definition here. So you take the simplex and you look at the neighboring simplex is a simplex which is contained in each other. So if you take that, that's as a definition of chromatic number. That's kind of easy to answer because it's just d plus 1. So in that case, we have just the minimal coloring is just a dimension function. But what we can do is, and that's what I looked in that paper here, we can look at the graph and we can look at the Whitney complex. If the Whitney complex is a sphere, so then I call the graph then a sphere. And in that case, we have this bound, and the four-color theorem tells you that in the case d equal to 2, and for spheres, for two spheres, it's between 3 and 4. And so that's a deep theorem in combinatorics. For 3 manifold, my theorem only gives just from between 3 and 6, but it's true for all manifolds, not only for spheres. And there are examples here indicated with 5, which need 5. For 3 manifolds, and that's this context here, question is there something with 8? So it's kind of an interesting question. For example, if you take a homology sphere, what is the maximal possible chromatic number which is needed? Is it 5? Is it 6? So these are the 3 questions, and I want to wrap this up.